Hello, this time I'd like to summarize the OT foundation analysis. The first half sections I explained that briefly LRFD design process of OT foundation. And the last half sessions I'm going to briefly introduce to that spreadsheet program for the settlement analysis and down deck load calculation. The first one, actually, there's two different pile types. If we assume that at the ground level, and there's a displacement pile, and another one, actually, non-displacement pile. So, displacement pile is actually, we call, actually, is a H pile. I'm sorry, it's a, CIP pile and timber pile. So, all these types of displacement pile. Yeah, H pile is actually, even though it's a solid pile, but we call it a non-displacement exceptional because it's the cross-section area is relatively smaller than the CIP pile and the pipe pile and the timber pile. Okay. So this is exceptional H pile. And non-displacement pile, then you put make a free borehole and then put in the rebar and then place the concrete. Okay, so this type is what we call the non-displacement pile. So it's totally different mechanism. And the friction, the driven pile actually has two different types. It's the frictional bear with me, it's poor my writing, and the bearing. Okay, so the frictional part is actually all the resistance coming from the side friction, like this. And the end bearing is on the majority bearing from that, the tip, the pile tip. So we just focusing the driven pile. Yeah, it's more, we just, presentation. Yeah, it's more neat. Yeah, drawing, it's good. So, as I mentioned, the upward frictions that happen, right? Or the driven pile. But in case you place some the embankment on top, actually, it's negative frictions are developed. Why? Because actually near the ground, surface ground, it's a settlement happen, so that it's pulling down the pile at the downward. So you maybe have some actually equalization point. So the below part is upward, and actually the upper part is downward. So that neutral planes we call the neutral plane. Okay. So neutral planes actually is located usually two-thirds of a pile length here for the frictional pile. If you end the bearing pile, all neutral plane is actually at the bottom. Okay, so remind that the neutral plane location. So it depends on the frictional and the bearing. So all LRT, the pile design is a start from the piece of that's just factored structural capacity. Okay, and that's just your baseline. Okay, so always you should have this type value before your design and for each candidate pile type, and you need to estimate the acceptable the structure capacity piece of R prime. So that piece of R minus actually the load factor multiplied this with B. So this is the downdrag load. We actually previous peak figure I explained that the downdrag load, right? So you negative skin friction at the upper part, and you multiply 1.4 usually the load factor. So this is the load, it's not resistance. So 1.4 for the static analysis. So usually the driven or the 8 pile, the unit pile, from the you get the downdrag load, you should multiply 1.4 here. And your actual factor, the structural capacity, should subtract by this portion. That's your available level for file capacity. So why this prime number is important? Because that actually calculated for your number of piles. So how many piles you're going to install? Your piece of R prime number is important, the capacity, okay? And how you calculate that length, okay? So that you did actually geotechnical capacity, R sub n, okay? That's geotechnical capacity. How you get that? Use actually your baseline number, P sub R, multiply reduction factor. This is a reduction factor. So it depends for if you using the static analysis method to evaluate the geotech capacity, you should multiply 0.4. Okay. So that's actually you getting from the static analysis. So you actually have known value this one and divide by this B here, and you're getting this number, right? Your R sub n. So from the static analysis, you actually getting the how deep the pile is satisfy this R sub n. So from the program, you estimate the pile length. Okay? That's important. And you actually need another important information. So, end of a pile driving resistance, R sub n, dr. This is different from the static analysis geotechnical capacity. Also, piece of starting point, piece of R. That's all you know that, right? And in that case, usually the end of pile drive acceptance is using the pile cap analysis, the pile drive analysis, PDA, pile dynamic analysis. Okay, so pile dynamic analysis case, and the P is actually 0.65. So you know that this value and divide by 0.65, you're actually getting this pile end over drive resistance. So this value is actually provided by your pile contractor. Okay, this is kind of your pile driving acceptance criteria. So this value is you can estimate from that relationship. And the last one, actually, you in your LRFD report, you should include that the drivability check. So drivability check. From the drivability check is you actually confirm under what's your acceptance blow count. Okay, blow count at the end of driving. And also, another important thing is a compress of tensional stress. So while the pile driving and that pile itself, the compressional tensional stress is not exceeding any the requirement required at that value. So your drivability check should include those two information. Okay. Yeah, actually, I posted 4 Excel program for your download calculation. So please take a look of the. So 3 spreadsheets for the settlement calculation, and 1 spreadsheet is for the calculation for your download load or the pile. So I will explain the settlement calculation spreadsheet first. And this spreadsheet is actually at the center location, the pile download load calculation. So the pile is actually, we assumed at the center of embankment. So you assumed that how much settlements happen in the middle of that embankment. Okay. So this spreadsheet is required you to put in input different soil types. So it's each soil layer, and it's specify the type here. And second column is you need what the starting depth for the depth each sub layer. And third column, and you need to input C sub C or C sub R. C sub C means purging compression index, and C sub R is a recompression index. So you should choose either of one, depends on to what the load level under that each the starting depth of a sub layer. And you plug in also the E sub 0, that's the initial void ratio of the soil. And C sub V is a coefficient consolidation. So from your lab test, you can plug in this value. And maximum C sub C and minimum C sub C is just a reference point. So it doesn't influence any your calculation result. Okay, it's just a reference for your reference. And compressor layer thickness, you need to plug in here for the soft clay and firm clay is actually compressible soil. So you total those 2 layer thickness is 23 meter. And drainage boundary condition is 1 is a single and 2 is a double. So a single is boundary is only top surface is only your drainage is allowed. You plug in the 1. But if you have this type of soil sand is located top and bottom, it's a sandwich condition, you assume that this is a double drainage condition. So in that case, you plug into 2, specify 2 here. And this section is help you out, evaluate that how fast that your consolidation degrees happen. So after maybe 6 months or 2 months, so 6 months actually you reach the 90% of consolidation, your actually drainage pass is 14 meter. And thicker the thickness drainage layer, is more lower consolidations happen, right, after 6 months. Maybe you change it to 2 months, yeah, it's much lower. Your thickness is actually get down. So after 2 months, actually 90% is only 8 meter, and 20% is 41 meter. Okay. And you can also check that this graph is it depends on that time elapsed, it's a month. How you actually specify that 23 meter the compressed soil layers excess pressure dissipated. So U is actually degree of consolidation degree. So reach the 100% settlements is get achieved. This diagram is showing the configuration of a new embankment, and so piles are supposedly located in the center of that embankment, and you need to specify groundwater depth. It's the depth starting point that usually from the ground, not from the top of embankment. And so gamma is supposedly all the soil, the unit weight is assumed at the same number. And so gamma is assumed the average value is 20 kilonewton per meter at this example. And the embankment actually has a plateau shape, and it's a side slope dimension. So side dimension is the extensions, you can just specify the B2. And your half section of your plateau area, the length is you specify B1. So this B1 is defined the half section, not the full length of embankment. Okay, keep in mind. And fill gamma is this new embankment fill materials, what's mean weight, and what the height of this new embankment. So 6 meters in here. And the program is automatically assigned depends on that depth from this depth is from your surface, not from the top of embankment. Okay, so below the surface ground is 1.5 meter. Is showing that to increase the in-situ stress, and also it automatically calculates the inference depth factor, multiply the loading embankment load. Actually, your additional load, how much load is applied on this each depth of the pile location. Okay, and you would need to also specify your pile length. So here is, for example, 30 meter, and the elastic deformation is the H pile. You just click to here, and the reference value is pi is 0.5 centimeter, and the H pile is 1 centimeter. Is for your recommendation. So elastic deformation, okay? So this C sub C sub R and initial void ratio is automatically assigned in your program. So you don't worry about this the value changes. Only you concern with this yellow input part. So yellow input part you need to specify. So you double check that this soil description is relevant to this soil table. It's rightly assigned. So you need to check that this sand, the soft clay, the starting point, and the palm clay starting point. It depends on this your embedment depth. And next, consolidation rate. That's it's an important concept. The 100% it does not allow any settlement. Okay, you plug in 100%. This layer is actually the program doesn't calculate any settlement. Okay, because it reached the 100% consolidation already. But starting point 0, so that means that your settlements happen from your 0 degree of consolidation, start to the 100%. If your clays maybe some over-consolidated conditions, previously reached some pre-consolidation pressure, then the only 50% of a consolidation degree is actually your starting point. Okay, so that in case maybe over-consolidate clay or some other specific case, you actually put in plug into this value other than 0. So 0 is actually most of the case at the normal consolidate, and maybe also clay or some previously consolidated conditions, and you should specify this degree of consolidations here. So your starting point of settlement. Yeah, so sand is definitely you don't need to account for the settlement calculation. So that's why you're plugging the 100 and the bedrock also. So those 100 value is not accounted in your settlement calculation. And your settlement, the next tab is showing the previous section is just load calculation, and the second tab is showing your settlement. Actually, how do you calculate the settlement amount for each soil layer? And this information is already copied from the previous section, so you don't worry about that. You just confirm that this information is matching with the previous tab. So only here the plugin value is the neutral plane depth. So you actually we assume that the end bearing pile. So maybe it's specify the neutral plane at the end of the starting point of the end bearing unit. And eventually you could get this where you getting the downdrag load, as we mentioned the previous video clip. The 1 centimeter above, that actually your relative displacement between the soil and the pile, that producing the downdrag. So this one here, right? So 1.1 matching is 21. So above 21, actually the relative displacement happen. So that whole pile upper section area is under influence of the downdrag load. Okay. And I added another spreadsheet. This is for the neutral plane the calculation. So from the BAO, the textbook, and you find that equation, and then you plug in the pile length and what the soil, the unit weight, and plug in, and the overall pressure over your embankment load. Okay, so how much embankment load you apply, and you eventually you getting, so this is switching point, negative to positive. This is your actually the pile length, the negative, the neutral plane location. This is for the center location, okay? And then I will show you, this is, the pile is located on the hillside, not the center of the embankment. You need using different spreadsheet. So that case is you actually, it's those sections the same as before, and then you plug in the soil type, and then the different degree of your starting point of consolidation degree. And you embankment dimension as you actually specify here, and then also it's another tab as you actually calculating. This spreadsheet you actually type in this C sub C, C sub R value separately. So OCR depends on OCR. It actually the spreadsheet choose which one, the C sub C or C sub R, for the depends on the OCR value and compared to the your shear stress. And void ratio value is also you need to plug in. So it's a little some cumbersome compared to the previous the engineering calculation sheet. So you plug in this C sub V, the coefficient consolidation, and you can also calculate how fast that excess pore pressure dissipate, and how the half range length is calculated for depend on the different of consolidation degree. And so that's the case is in the pile location along the hillside. And the last the spreadsheet is the pile is located outside of the whole embankment. So that separation length is from end tip of this slope to your pile location. Okay, so this configuration is like that. You specify the outside distance from your embankment, the pile, and this assumed the more simplified. It generated, it assumed the whole the layer that's the over-consolidated clay or normally consolidated clay. You just differently specify this value, compression index, and excuse me. And per the different months, you actually calculate also half range path for your reference. Okay, and then last one, those three based on the settlement calculation, you actually calculate the boundary load. So if a driven program is not available to you, you need to use this the static analysis spreadsheet. So you specify the pipe pile and H pile. So you specify the depth, the pipe pile, the diameter, and the H pile is actually you just the conversion of the H pile. So the definition is 2 times the flange width and multiply width and flange and divide by the pi. So your conversion value actually. So the processes anyway is basically same. Okay. So only just the pile section is different. You actually plug in those soil property depends on that soil layer. And then if you need to include those piles, but remind, you should select those parameter, shear strength parameter, either P or underlying shear strength. You choose either one, not to both of them, okay? So only one value is applied those pile analysis. And the analysis steps is default base of 0.5 meters, so every 0.5 meter, and you actually get the side friction. So side friction from your non-cohesive type and cohesive type side frictions you can separately calculate, and total side friction. And this is the end bearing unit. You're actually getting also end bearing capacity. So final value is actually add up with side friction and the end bearing H price also. So please read through those before you do the analysis and read me section. So how you should apply the right value for you getting down the load. Okay. And good luck if you have any question, feel free to ask me.